My name's Michelle Frost. This is the elephant in your dataset, addressing bias and machine learning. That's Wilbur. He's a good boy. Much better up there than me. By day, I'm a senior developer for Crema. We're a software consultancy in Kansas City, Missouri, and by night, I'm a grad student at Johns Hopkins studying AI, and I graduate in 4 months. So I'm very excited to go back to having one job. It's a 2-clicker, okay. So here's our agenda today. We're gonna start off with a little bit of an exercise. And then we're going to talk about what is bias. What is it when we talk about it in society versus in a machine learning life cycle? And what are the different types of harmful bias? How has bias in AI systems caused harm? How can we quantify bias? How can we mitigate bias? And then we're going to go through a demo. So a couple disclaimers. This is a lot to get through. We're going to go very wide but shallow. Know that every single one of these items, of these questions, could be a talk of its own. So what I hope is that this kind of sparks some intention to go and do some further research. So the other thing, the other disclaimer, how has bias in AI systems caused harm? We're going to have some examples. And I don't take out the name of the company because if I did, then you guys would just be Googling trying to figure out who did this. There's some big companies here. Some of you may work for them. And that's okay. They're not to, this isn't to call them out and say what they've done is bad. It's just to show that this can happen if we're not intentional about how we carry on. And so our goal today is for every attendee to leave feeling empowered to answer these questions and be able to be an active participant in discussion of bias in AI systems. So next up, we're going to do a little exercise. A couple of you guys might be uncomfortable. If you become uncomfortable, I would challenge you to ask yourself why and maybe sit in that, right? So hopefully this comes up here. This is an intersectionality, a wheel of privilege. Now, these are privileges as observed in the USA, so this is going to differ a little bit. But for the most part, I think that these are pretty generalized. So as I go through here, just kind of ask yourself if you occupy this space of privilege. Okay, and I'm not going to read through every single one of these because we'd be up here the whole time, but note that in the middle, we have a space of power, okay? That's the dominant and, again, observed in the USA in each of these subsections. In the middle, we have what we might say erased. So there's not a sense of power, but there's also not a sense of being marginalized. And then on that outer rim is a marginalized group. So if we go clockwise, skin color, neurodiversity. Are you neurotypical, neurodiverse? Mental health, are you stable? Physical ability, are you able-bodied? Religion, again, varies from country to country in the US. Christian. Wealth, age, education level, housing, are you housed? Do you own a home? Transportation, do you have access to a car? Can you get wherever you need to, whenever you want to? Political affiliation, again, this is going to vary across different cultures, different geographic areas. Marital status, citizenship, employment, language and communication, sexuality, gender, and body size. These are all spaces of privilege that we can occupy. And it's important to kind of understand where we sit here because if you have a privilege, you might have a blind spot. And if you have a blind spot, you can inject bias, intentionally or not. What is bias? Well, generally speaking, when we talk about it, it's an inclination or prejudice for or against one person or one group. Now, in machine learning, it's a systematic error that occurs in the model itself due to assumptions made in the ML process. And I mean, of course, because we weren't going to get through this without one. Now, biases, we talk about it in many different ways. It's not always bad. So I have to preface this talk saying that sometimes it's necessary. So we have what's called inductive bias. So machine learning is a search process, right? And a search process needs a set of assumptions to guide the search, otherwise it would be blind. So this set of assumptions is what we refer to as inductive bias. And this is a more formal quote from a 1997 paper by Tom Mitchell. It's a set of assumptions that, combined with observed training examples, deductively entail subsequent instance classifications made by the learner. The other bit we have to talk about is the bias variance trade-off. Now, in machine learning, we have a lot of different types of trade-offs. So I'm going to talk about another one very relevant to this talk a bit later. But you have, I'm sure we've heard of overfitting, we've heard of underfitting, right? So overfitting is when we have very high variance. Maybe your training data set is performing very highly, right? Because it's learning those examples in the training data. Whereas when we have a high bias, we tend to underfit. Okay, one more prefacing slide before we get into the meat of this. Some bias terminology. Okay, so we have a protected class, which is a category where bias is relevant, and a group is likely to be differentially affected. Sensitive characteristics. These are the features, the algorithmic decisions where bias could be a factor. Disparate treatment is when members of the protected class are treated differently, and then the disparate outcome or impact is the effect of that treatment. So to introduce bias in machine learning, I'm going to use a paper that came out in 2021 by Suresh and Gutag. And what they did is they identified 7 different potential places where we could inject harmful bias in the machine learning life cycle. So this should look pretty familiar to us. The first half up above is the data generation flow. Down below, model building and implementation. Here are the 7 places that we could inject bias. We're going to go through these one by one and talk about them and then show an example for each. But of course, we have our historical bias, comes from data generation. We have representation bias. We have measurement bias. Okay, these are all in the data generation. And then we start kind of, let's say you're 11 o'clock, counterclockwise, aggregation bias, and then learning bias, evaluation bias, and lastly, deployment bias. Historical bias. This is probably the easiest for us to predict, right? Garbage in, garbage out. Even if the data is measured perfectly, sampled perfectly, if the world as it is or as it was has prejudice, then it's going to lead to a model that has harmful outcomes if you don't mitigate them. Gender bias in ChatGPT. There's actually a lot of different biases in ChatGPT, but this is a particular study by Dr. Kodak and Dr. Ravit Datan, where they were interrogating ChatGPT to try and get it to say that a doctor could be a woman and a nurse could be a male. And so they set up these sentence structures to where they could swap the pronouns out. And even when it did not make sense, ChatGPT still said that the nurse was female and that the doctor was male. You can do the same thing. Tell me a story about an engineer. It's going to tell you a story about a man. Tell me a story about an engineer named Michelle, and it's going to go and tell you how I fought against the patriarchy. Same thing. Tell me a story about a nurse who is a man. It's going to say how his family wasn't sure if nursing was, the right fit for him, and this is within ChatGPT. So next we get into representation bias, and this is when a sample underrepresents some part of the population and it doesn't generalize well. So it's problematic when the target population does not reflect the use population, or if that target population contains underrepresented groups. or if the sample method is limited or uneven. So, it's easier for us to imagine this. You've got a sample, you've got the pink dots, you've got the blue dots. How do you think it's going to perform on the blue dots? Thank you. Anyone remember this one? Google started identifying African Americans, Black individuals, as gorillas. An engineer discovered this, posted it on Twitter. Does anyone know how they fixed this? They removed gorilla as a label. Yeah. Measurement bias. So when we're choosing, collecting, or computing features as a proxy to represent some construct, remember that we're guessing here in some cases, right? It's easy for us to say an apple is an apple, a pear is a pear, but what about when we're measuring things like creditworthiness? Can we really say that we know which features will belong to that? And so this becomes problematic when we have an oversimplification of a more complex construct. If the method of measurement varies across groups, and if that accuracy of measurement varies across groups. Who here has heard of COMPAS? So this is COMPAS, Correctional Offender Management Profiling for Alternative Sanctions. Okay, this was developed by an Illinois company in the late 90s called Northpoint, and their goal was to help judges determine if bail should be set for offending criminals. And so it's predicting recidivism, right? If someone that's committed a crime is going to go and commit another crime. Does recidivism, though, truly indicate the presence of a crime, or does it indicate the presence of policing? Is it the right measurement tool? So this went into effect, and the last I checked, it was being used by 49 out of 50 states, by the way. It wasn't public, or it was not independently reviewed until 2017 when ProPublica took its findings. They spent about a 2-3 year study looking at the different data. And what they found was, though, as Northpoint reported, the average accuracy between white and Black defendants was about the same. The types of errors were very different. So labeled higher risk but didn't reoffend. Let's see if I can, right there. So whites, 23.5% error compared to 44.9% error for Black individuals. Labeled lower risk yet did reoffend. White, 47.7%. Okay? So our false negative for white defendants was almost twice as high as Black defendants, and our false positive rate for Black defendants is almost twice as high. Now, it's worth noting that Northpoint rejected ProPublica's claims, saying that they interpreted the types of errors incorrectly, but there's been lots of studies done, in particular about COMPAS since that time. Okay, aggregation bias. This is the assumption that a one-size-fits-all model can map inputs to labels across all subsets of the data, right? So if a data set represents people or groups from different backgrounds and cultures, a given variable might mean something different for them. If we were running some sort of a text classification, okay, on my phone maybe, and maybe we're trying to identify risky behavior, and I've shot out a text that says, I'm gonna be late, I'm on LSD. So you guys are probably making two assumptions. Number one, I'm on drugs, and number two, I've made bad decisions. Has anyone been to Chicago? Worst street to drive on is Lakeshore Drive. We call it LSD. I've still made a bad choice, but I'm probably not on drugs. This also comes out in healthcare, okay? There was a big study a couple years ago. There's different levels of hemoglobin performs differently across different ethnicities. So if we don't account for that in our systems, we're going to have varying results across different subsets. Learning bias. When our modeling choices prioritize one objective that damages another. Remember we talked about that trade-off? So this comes across not just bias variance, not just accuracy and fairness. We'll talk about that, but you know, if you prioritize accuracy, you might take a hit in disparate impact. So if we minimize, for example, our cross-entropy loss for classification, that might lead to a model that has more false positives. Amazon. This was big news in 2018. They created an AI hiring tool, and it immediately started saying that the women weren't going to do the job well. This was especially prevalent across the technical and engineering roles. So then we start to evaluate our models, right? We want to see how they're performing. But we do that often against benchmarks, right? What if that benchmark data doesn't represent the use population? Things like below average, average, above average, those are really subjective, right? So if we don't start looking across the wider group and into individual subsets, they're not going to perform very well. Project Gender Shades, I highly recommend going there. They have a beautiful website. And they did studies on facial recognition performance across three main, IBM, Microsoft, and then Face. And so if you look at this, the biggest difference in error, and again, this website, beautiful UI, and it'll dig very specifically into the different types of error, but there is a 34.4% difference between a white man and a black woman from IBM. That was the largest gap of error. Last but not least, deployment bias, okay? What if we intended to solve a problem, but somebody else is using it in another way? We can also look back to that compass, right? When they developed it, they wanted to help judges determine if and what bail should be set at. But then courts started using it to sentence. That wasn't the original model, but as engineers and as stakeholders, as anybody engaging with a product, we have to think about how it can be incorrectly used. I have a slide for recommended reading at the very end, but specifically Virginia Eubanks, Automating Inequality. She looks at 3 different cases where we built an AI system and it failed poor families. So in particular, a very alarming one was a child abuse prediction model. Okay, if you look at a middle-class family and a child is being left in the cold, okay, maybe we should look into that, or if they're not being fed often enough. But what about for families who can't afford that same thing? So what are we going to do about it? Well, can't we just omit all the protected attributes? No, you cannot. So we can explain this through Simpson's paradox, which gets pretty technical. It's a statistical phenomenon. But basically what it comes down to is that our features have been so bled in, right? Even if we take something out like, let's say, gender and income, we have other features that attribute has bled into, right? Because our data is entangled. So we can't just take out one feature or one column and expect to get unbiased results. We also have to talk about explainability here, right? Because the more complex our model is, we might gain accuracy, but our explainability is going to decrease. We're going to have a harder time figuring out why we have bias in a model, why certain groups are performing differently than others. And we need to be able to explain them, right? Especially in relation to human-affected applications. So this brings us to fairness. my particular favorite area of research in responsible AI. And basically what we're doing is we're trying to study how to ensure that these biases and model inaccuracies don't lead to models that treat individuals unfavorably due to sensitive characteristics. Another meme for you all. 2017, 2016 was like the year fairness papers exploded. That trend has kept going. There's new fairness papers coming out all the time, and there's some really fabulous work being done in the area. So before we start getting a little technical, we'll just do a brief review of the different types of errors. So we want to compare what our predicted values were, right, against what the actual values are. So we know true positive, true negative, we got it right, okay? False positive, we predicted positive, it was negative, false negative, we predicted negative, it was positive, okay? I think this has become a little bit more public too since the COVID test came out, right? You can kind of start thinking about which false you'd rather get, depending on the circumstances. So there are about 20, I'm gonna misquote myself, between 20 and 25 different types of measurements for fairness, okay? A lot of people have been working on this, but there's really 3 that we want to understand. So first, statistical parity. 2012, DeWork came up with this definition, and this is achieved when the decisions or outcomes of a model are independent of a protected attribute. Now, something to note here is that this is caring about the predictive equality, not the ground truth, okay? So we want to see that we're accurately favoring women and men for a positive prediction, okay? We want to have that to be kind of balanced. And the difference is going to be what that difference is. We can also look at it in a ratio. Then we're going to get into the most restrictive concept, okay? Equalized odds. Now we do care. We care both about our predictive equality and what that ground truth is. And equalized odds can only be achieved when the true, that's a typo there. The true positive rate and the false positive rate are equal across different groups. Okay, so we can use this when we want to place a strong emphasis on predicting the positive outcome correctly, or if we want to minimize a costly false positive, or if the target variable is not subjective. And Hart et al., 2016, came up with this definition, as well as equal opportunity, which is a very specific instantiation of equalized odds that measures fairness in terms of the true positive rates. Okay, so if we want to predict positive outcomes correctly, okay, so like that recidivism task, that might have been important. False positives are not costly. Target variable is not subjective. We can also, there's another predictive equality that then measures the true negative rates as well. But that one's not used as heavily. So what are we going to do about it? Mitigation strategies. This in and of itself could be a workshop, okay? We can divide the mitigation strategies into basically 3 different points, okay? Pre-processing, right? So we want to apply mitigation to the training data itself. I don't have any examples up there because I'm going to walk through several in a demo for you all. In processing, so we want to do this during model training, okay? So one example, adversarial debiasing. We all know what GANs are, right? Generative adversarial networks. It kind of performs the same. You loop 2 up together, and one learns to maximize the prediction accuracy, and then and you want to reduce that adversary's ability to determine the protected attribute from those predictions. We can also put in what we call a prejudice remover, which is a discrimination-aware regularization term. There are other methods as well, like using multi-objective optimization to look both not only at accuracy, but also fairness, okay? Then in post-processing, we want to mitigate after training, equalize odds, so we could change the output labels, we could classify the reject options and give favorable outcomes to underprivileged groups. In my mind, this is a little bit like trying to retroactively fix the problem, right? We really want to do it if we can, at the data layer or during the model training itself. And if we can get this right and we can get enough people to use it, then we can start deploying this in highly used production systems. Demo. Okay, this is the part where we hope it works just fine. So we are going to pause this one, bring her up. And mirror. And it's very small. Great. So let's do this. And it's still kind of small, so. It's still kind of small, but we're going to walk through it together verbally. Come on. I was trying to minimize it just a little bit. That's fine. So this is a data set. It's on the UCI machine learning repository. It's called the adult data set. Perhaps some of you guys have heard about it. I would never use this thing in production because it's really antiquated and it's just not great. But it's used a lot in studies on fairness because of the differences. So the adult data set was trying to predict high versus low income. And now they define that as being at 50K USD. I think that this data set was compiled in the 90s, if I'm not mistaken. So obviously we would do this a little bit differently. But the reason it's used so frequently is because there are a lot of protected attributes in here, okay? There's race, there's gender, there's education levels, marital status. We could dissect each one of these and see how bias performs against each one. So you can kind of get a little look there. And so let's just kind of look at some of these different groupings, right? Our female to male data samples, not good. Our bias example is going to look at gender, but I'll show you guys a couple different other groups as well. White observations. United States, countries. We've got just barely any representation from anywhere else. The next one right here it's Mexico, so. Same with education levels. We have a lot that are high school grads. We have very few in preschool, some college. This varies a little bit better, but it's not great. Different types of working. And then this is our target column. We've got like a third in the positive column, right? If we start looking at this by gender, we have barely any females in the positive outcome. Compare that, just to the ratio of the male. They're a little bit more balanced, right? Still pretty off, but a little bit better. Same if we start looking at this by race and gender, how the different groups perform. And then I magically pre-process this data set for you all, because that's not what we're doing, right? Okay, so if we just run a general logistic regression on this, we get an average accuracy of about 84%, okay? So without debiasing, pull this down here. So our accuracy for female 91%, almost 92%. Not bad, right? Why is that? Because it's pretty safe to say that they're going to be in the negative column, right? So here's what we're going to start looking at through the rest of this demo. These are our rates, and I know it can be a little hard to see. So remember that orange is false positive, and red is false negative, okay? We hardly misclassified that false positive for the female group, right? Our false positive for males is much higher, which makes sense because there's more males in the positive class. That's a note to Michelle to go to the dashboard because I forget it. Okay, so this is a tool from Microsoft. On GitHub, they have a responsible AI toolkit, okay? There's a lot of different things to kind of explore and play around with in here. But what I have here is their fairness dashboard, which comes from their responsible AI widgets package. And this is really cool because you can set it up. I will tell you that there's some package difficulties with this, so you have to run it on a separate virtual environment. But it lets you upload your model, select your sensitive features, and then you can start looking at different performance metrics by either difference or ratio. So if I get started, so we're looking at if we're male. Let's go ahead and look at balanced accuracy. And we talked about demographic parity difference. We'll click around through a few of these. And then what I want is the false positive and false negative rates. Okay, so the top bar is our female class. Bottom bar is male. Orange is our false negative rates, and blue is our false positive rates, okay? So we've got a pretty big gap there. And if we're looking at the demographic parity difference, it's 19%. What are we going to do about it? So if we're looking at pre-processing mitigation techniques, there's a couple ways we can go about it. Now, remember I told you all that unawareness doesn't really work, right? We can't really just remove that protected attribute and expect that it doesn't know about it. So proof here for you. Our overall accuracy stayed about the same. The accuracy for females, I think, dropped just a tad. And overall, we're still looking quite the same, right? Our false positive rate for females is still much smaller than it is for males. False negative rate still higher for females than for males. Okay, so what if we balanced it, right? What if we made sure to take the same number of males as we do females? We get a teensy bit better, maybe, but not by much, right? Why is that? Because the target is still the same, right? We had an imbalance in the target ratio. So what if we do that? Okay, we're starting to get better. Something to keep in mind here, though, remember how small that female class was compared to the male? Remember how small that positive female class was compared to what we had available for the male class? If we do this, we're limiting our data set to the maximum of what we have, right? Which wasn't very much. So we just took our data set and we took a small percentage of it. And that might not be realistic when you're in a production use case and you need a lot of data. Still, we should know about these things, right? So if we start looking at the rates here, so the false positive rates for female, 0.07. False positive rates for male, 0.1. Not perfect, but we've gotten a little bit better, right? False negative rates are super close, 0.08 difference. We're looking better. Maybe we'll take this. Okay, there's another group that says we can do counterfactual augmentation because you can't take out that attribute, right? But what if you flipped it? So then what we're doing is instead of saying that, that we have that Simpsons paradox where it's bled into other places, we kind of confuse the model because of what it thinks it's learned about that gets flipped on its head. And if you look at these numbers, they're pretty close, right? Why would I not recommend using this in production? Because you're flipping the labels on their heads. So it's great for a study just to prove that we can do it, but I wouldn't recommend doing this in a production system. So let's go down here and check these out. So our X's are our females, our dots are our males, and we can kind of start to see where we're mitigating those differences in the rates, right? So on the left, that was our original, and moving over to the last two, we have our balanced ratio and the counterfactual arguments, and we're getting that circle and the cross very close together now, aren't we? It's almost indistinguishable on that counterfactual version, but again, I would say use caution if you're using that method on a real data set. Okay, so this is another instantiation of the fairness dashboard, and we're looking at the balanced target ratio. Again, I wanted to show you guys the counterfactual, but we're going to look at something that would be a little bit safer in production. So we're going to hit balanced accuracy again for parity, and we'll look at these false positive and false negative rates. It's not perfect, but it's a lot better than that, okay? Our difference went from 19% to 1.08%. Now, demographic parity might not be the right metric, right? We talked about these metrics. We talked about when they make sense to use them and when you need to dig a little bit deeper. This fairness dashboard lets you look at other things too. So let's look at the equalized odds ratio for both of these. Excuse me, the difference. So equalized odds difference in our original unchanged model, 15.3%. Come on. And it goes down to 5.16%. So it's getting better. Now, this is the tricky part. This is where I have a lot of things for you guys to take photos of. Book recommendations. I could probably add to this, but these are my top 6 favorite. So starting on the top left, Weapons of Math Destruction, Cathy O'Neill. If you haven't read this, it's absolutely fabulous. It looks a little bit more from a statistical perspective, but she talks about a lot of different use cases where we've created some sort of statistical model that caused harm. Biased, again, not super technical. It's a quick read, but it's something that we need to think about, right? We looked at our privileges. We thought about that. Bias is going to dig a little bit deeper. It also talks a lot about that compass system that I mentioned. The alignment problem is a lot of fun. Brian Christensen, and he kind of talks about that. So, when we're talking about AI systems, how do we align the need for a robust system and an accurate system with how is it going to impact society? How is it going to impact individuals that, it's making predictions on? And he talks a lot about reinforcement learning too, and the psychology behind reinforcement learning. So if you want to nerd out, it's a good place to do it. Invisible Woman, you can kind of guess what this is about. Data bias in a world designed for men. The Big Nine, Amy Webb, one of my personal favorites. So she wrote this in 2019, and it's super relevant. She goes through the history of AI and kind of talks about how we got to where we are today. and it's a lot of fun. And then again, I mentioned automating inequality, Virginia Eubanks. So again, I work for Crema. We're a design and technology consultancy that exists to help enterprise leaders discover, understand, and execute on your greatest opportunities. That QR code will get you a contact form in case you would like to talk with us. I am also a member for the Center for Practical Bioethics, Ethical AI Initiative Services. We're based in Kansas City. We're looking to expand. We work with different healthcare organizations on sort of a three-pronged process. The first is education and training for both healthcare providers and developers in their organizations. Then we look over executive level supports. How do we help C-suite executives make the right decisions? Sometimes the word ethics scares people, so we talk about risk instead. And then our process improvement tools. What kind of processes, checkpoints, lifecycle mappings can we put out to help organizations understand these processes? And if you'd like to get in touch with us, here's another QR code for you. Ethical AI Council. Give me just a second there. And then if you want to talk with me, that's me. Appreciate you guys all being here. Like a final comment before I open it up to questions, which I think I did pretty good on time. So fairness, it's not just a byproduct of algorithms, right? It's a choice that we have to make. Sometimes it's akin to choosing a harder right over an easier wrong. But as developers, as engineers, as stakeholders, we must go into the products that we're building and advocate for this. And we saw that a little bit of that accuracy fairness trade-off. But in order to achieve fair systems, we have to be willing to sit in the middle for a little bit, right? Questions, comments, concerns, cheap shots?